So now we come to Lagrange multipliers and equations of constraint. What we've seen so far is that we've identified degrees of freedom, and then that has led to generalized coordinates. And so we've got the Lagrange equations, and so d by dt of the partial of L with respect to q dot minus dl dq. Then A is the subscript that describes the degrees of freedom. And then that has been set to 0. And so this is where we've identified all the degrees of freedom and then associated them with generalized coordinates. But the real power of Lagrangian mechanics comes when there are constraints. And I'll just give a really simple example. And so let's just look at a bead sliding along a wire without friction. And this wire has some shape to it. And so there's the shape of the wire. And then on top of that, or on that, we've got a bead which is sliding under gravity. Okay? And so we've got an equation of constraint because we have a function f of x and y equals to 0, right? And so that's a function that describes the shape of the wire. And so if we were to try to do this with a free body diagram, this would be a really tough problem. We would have to look for tangents, we would have to look for the component of gravity along the tangent. And this is where the power of Lagrangian mechanics comes in, and it comes in through the power of multipliers. And so they are also called Lagrangian undetermined multipliers. They're undetermined initially, but what we're going to see is that in these mechanics problems, it's going to allow us to derive forces of constraint. So not just so, we give the path of constraint, but then we're going to get back out forces of constraint. And that's something that would be actually difficult to get out in any other way. All right, and so what's happening here is that forces keep the bead on the wire. Okay. And the other thing that's important here is that x and y are not independent. And what I mean by that is that if I have motion along x and y, in fact, let me put those. So here's x and here's y. So if I have motion in the plane, in general, I've got two coordinates, x and y, that I'm using to describe the motion. And if we didn't have constraints, we would actually have 2 degrees of freedom and 2 generalized coordinates. Now that we've got this curve, that the bead has to be on this curve, it's really a pseudo one-dimensional, although we don't really want to use that word of one-dimensional. I mean, what we really want to say is that we've got a mechanical system that has a single degree of freedom. And the single degree of freedom, in this case, is just going to be the path length as it slides along the wire. Okay? And so another way of saying that is that we've got a manifold. So we've got an embedded, or an embedding space that's 2 dimensions, that's the plane. And in that space, we've got a one-dimensional manifold is embedded in that space. And so we've got 1 degree of freedom. So the way that this problem is going to work is that we're going to actually keep x and y as if they were 2 degrees of freedom, but then we link them through the Lagrange multiplier, and that's the equation of constraint. All right, so let's go to the variational integral, since that was the starting point of Lagrange's equations. And so we had derived that d epsilon is going to be equal to this integral sum over the degrees of freedom, or actually I don't want to say degrees of freedom anymore, sum over the generalized coordinates. Okay, so we define some number of generalized coordinates, and then there's going to be some equations of constraint. So A is the generalized coordinates. d by dt of the partial of L with respect to q dot A. And then we've got subtracting dl dqa All of this is multiplied by the variational or the variation function eta, and then integrate over dt. All right, so that was the end of the derivation that led us to Lagrange's equations, the Euler-Lagrange equations. But now we've got a force of constraint, all right? And in fact, we may actually have a number of forces of constraint, because now let's actually get away from the problem in the plane. Let's actually work this generally. So now this index A is something that can go over many generalized coordinates, and at the same time, we can have equations of constraint. So we're going to have f sub b, where b is going to be another index. I could have 1, 2, 3, 4 equations of constraint, as long as the equations of constraint is less than the number of generalized coordinates. And so what that means is that I want to define a differential on this force of constraint. So let's look at df. And so df, I can expand that in terms of the generalized coordinates through the Jacobian, right? So here we've got the Jacobian, and then I'm going to have dqa, d epsilon, and then I'm going to have d epsilon, okay? And what I want to say is that this is 0, all right? And so the variation on the force of constraint is 0. Well, if we go and look at the derivation for the Lagrange Euler equations, we actually ran into that, this term right here. And it turns out that this is actually eta of A, right? So this is eta A of t. And so what that means is that I can actually put that, I can put this differential to force into that integral, because that differential is actually 0. So I'm just adding 0 inside the integral. And so what I can do is rewrite the integral. All right, so let me rewrite the integral di d epsilon. And that is going to be equal to sum over A, integral, sum over A. We've got d by dt, dl, dq dot A, minus dl, dqa. And now all I have to do is just add in this equation of constraint, but I don't know what proportion to give it. It's 0, or the variation is 0. And so it is going to contribute in some way. And let's just say that there's going to be this undetermined multiplier. It doesn't, you can multiply anything by 0 and you still get 0. And so I can multiply the differential by that lambda. It's still going to be 0. And then I'm going to have, and in fact, let me, since we are talking generally, since I have several equations of constraint, let me sum over those. I'm going to have a Lagrange multiplier for each, and then I'm going to have dfb, dqa, and then end the paren, eta a of t, and then dt. And now we have an extended Lagrange's equations that includes equations of constraint through the undetermined multiplier. And so we'll just write down the new Lagrange's equation. And so we've got the d by dt, dl, dq dot a, minus dl, dq sub a, plus sum over b, lambda sub b, f sub b, or df b dqa. And then this is equal to 0. And this is such an important equation that, I mean, this extension, right? So what we've done is we have extended the formalism of Lagrange's equations so that in some sense we no longer even have to identify degrees of freedom. We just have some space that could be described through generalized coordinates, or we have this mechanical system that can be described through generalized coordinates, and we've got some number of equations of constraint. And so we're kind of free to pick our generalized coordinates, whether they actually end up numbering more than degrees of freedom for the problem. But those extra sort of coordinates will be reduced by those equations of constraint. And so I also do want to say then that we'll have that A is then going over the number of generalized coordinates. Let's say we've got n generalized coordinates, but then B is going over the number of equations of constraint. And so the degrees of freedom is actually n minus m. Yet what we'll have to do is solve equations for n plus m unknowns. Okay? And so by adding equations of constraint, we end up with more complicated equations. We have more unknowns that we have to solve for. The number of degrees of freedom actually stays constant, right? I can add more generalized coordinates, but then that would require us to add more equations of constraint, for the same mechanical system, right? So there is kind of a balance here. And so you don't want to add too many equations of constraint so that you don't get too complicated in your problem. And so typically what we'll do is work with problems that have, let's say, ropes, and there's tension in the ropes, and the undetermined multipliers will allow us to say something about the tension or about the torque that is causing a cylinder to roll down an inclined plane and things like that. All right, so let's actually start looking at, well, I tell you what, before I do that, in fact, I ran out of space here, so let me just sort of add one final kind of comment just to make this concrete. And that is that what we really have now is this Lagrange equation, d by dt. I'll do dl dq dot a minus dl dqa. And I'm going to say, okay, that's going to be equal to a generalized force. And so this is the part where the Lagrange multiplier comes in. And so that's the sum over b, lambda sub b, dfb, dqa. Okay? And so this is the way of thinking about how the equations of constraint come in that we have them introducing generalized forces that now go along with our generalized coordinates. Okay, so having said that, let me now move to examples. Okay, so we're going to go through a set of examples, and these are going to step up in complexity. And so number one, it's just going to be a bead sliding down a straight wire that's at some angle. Okay, so let's set that up. So this is in y and x, so that's our space in which this problem is embedded. I've got a wire which is going up at some angle theta, and then on that wire I've got a bead which is sliding without friction, right? So it's going to be sliding without friction, but subject to gravity, so it's obviously going to be sliding to the left and down to the left here. Now the equation that I'm going to use here is that y is equal to tan theta, that's just the slope, times x, okay? So that's the equation of the wire. Now I need to express that as an equation of constraint. I need to have an f which is equal to 0. So that means that I'm going to define f as y minus tan theta times x, and then that is 0. Okay, so that's my equation of constraint. I have to write it in a form in which f equals 0. Okay, so like all these Lagrangian problems, what we'll do is build the kinetic energy. And so that's going to be 1/2 mx dot squared plus 1/2 my dot squared. All right, so I still have two generalized coordinates here. I've got the bead is changing in x and it's changing in y, so I've got two generalized coordinates. My u, in this case, it's just gravity, which only depends on the altitude y or the height y, and so this is just going to be mgy. Okay, so there's my u. All right, so we put those into these extended Lagrange equations, and so let's just do the first one, d by dt. it's going to be, I'll just write this out all explicitly at first. As we go through these problems, I'm going to sort of skip more and more steps. And so I've got dl dx dot minus dl dx minus lambda, and there's only one equation of constraint, so I don't have to put a subscript. And then this is df dx, and that's 0. So let's just go ahead and start to evaluating this. All right, so the d by dt of the dl dx dot, that's going to be mx double dot. And then there is no dl dx because there's no x dependence in the u. And so then I come to the lambda df dx. There's a minus sign in it. And so this gives me a plus tan theta times lambda. Okay, let's do the second equation. D by dt dl dy dot minus dl dy minus lambda. There's only one equation of constraint, right? So that's the same lambda, but I do have a df dy. That's 0. We just go ahead and evaluate that. That's going to be my double dot. And I have, in this case, I do pick up an mg from the potential, and then this just becomes minus lambda. Okay, because if you look at the equation of constraint, it just depends on y. Okay, and so df dy is 1, and then I've got the lambda for the multiplier. Okay, and so that gives me 2 equations here. So let me actually number those. And so this is equation 1, and this is equation 2. Equation 3 is the equation of constraint. So let me just write that down again down here. And so then I'm going to have that y. In fact, let me do this in blue. Y minus tan theta times x equals 0, and that's my equation 3. Okay. All right. Because I do have 3 unknowns. The 3 unknowns are x as a function of time, y as a function of time, and lambda as a function of time. And so I have the 3 unknowns. In fact, let me just even write those down. So I've got x, y, and lambda are the 3 unknowns I need to solve for. And I've got 3 equations, so I'm good. All right. So what do we do first? All right. So there's kind of a, I hate to use the word trick. There's a trick. It's not a trick. It's a sort of it's things you want to do systematically and consistently, sort of problem by problem by problem, so that you become really comfortable and a lot of the problems start to feel the same. So the first step, not trick, but the first step is let me take my equation of constraint, that equation number 3, which is that y minus tan theta times x equals 0. Okay, so I got that. But if we look back, you know, my other 2 equations actually have the double dot. All right, they have this double time derivative on it, whereas my third equation doesn't. And so at first that might seem like a problem because it looks like I've got 2 equations that are second order time derivatives and the third equation isn't. But that's easy to solve because all we have to do is take a second time derivative, and I get y double dot minus tan theta times x double dot equals 0. And so I'm going to call this 3 prime. All right, so that's your equation 3 prime. This is pretty consistent across lots of these problems. So you've got your 2 dynamical equations coming from Lagrange's equations, and then the third equation that we need, because we have 3 unknowns, is the equation of constraint. But all we need to do is take the double derivative, and now it's expressed as y double dots and x double dots, and the equations of, the mechanical equations are also x double dot, y double dot. Now we've got systems of 3 equations, 3 unknowns, and they're all to the same order. And so taking a double time derivative of the equation of constraint is no problem. In fact, that is the standard step, and so that's what I call the trick. Okay. So now we're in actually good shape. We have the 3 equations. So let's just start to solve them. Now, I mentioned last time, I said if you ever find yourself doing substitution, stop and use Cramer's rule. Well, okay, that's actually not always true. sometimes the substitutions are so simple, you might as well just do the substitutions, okay, when you're solving multiple equations, right? So let's just go ahead and do that. And so let's actually take the first equation and the second equation, and let's actually just solve for lambda, okay? So let's just first solve for lambda. So the lambda is going to be my double dot plus mg. It's also going to happen to be m tan theta times x double dot plus mg. Okay, so lambda is going to be equal to both of those, and so it means that the two dynamical equations are actually equal to each other. And so we can go ahead and just go ahead and do that. So let's just then use the second set of equations there, and let's just do a little bit of algebra on them. And so that gives me an mx double dot plus tan theta times m tan theta x double dot plus mg equals 0. I've just combined the last two equations there. That looks kind of ugly. We'll just do another step of algebra on this. And again, like I said, as I go through these problems, I'm going to skip more and more steps. I'm just going through everything here. So mx double dot plus tan theta. Oops, just repeating myself. So mx double dot 1 plus tan squared theta plus mg tan theta equals 0. And then finally, let me just write the final, after a trig identity, this gives me an x double dot plus g sine theta cosine theta equals 0. And I'm just going to do the same thing for the y. And so I get a y double dot plus g times sine squared theta is equal to 0. So here are my equations for x double dot and y double dot. Okay, so I've got, and those are separated now, right? So those aren't coupled anymore. So I've got two second order differential equations for x and y. And that's the solution to this problem, okay? And so what we're trying to get out of the Lagrange equations, a lot of times we won't give it some, we're really looking for equations of motion, right? So we're looking for equations of motion that describe the system. And then once we get them, we can either find analytic solutions if we wanted to, or we can put it into a lot of these will turn out to be nonlinear, and so we can put them into a nonlinear ODE solver. But the main goal is actually to get the equations of motion, not necessarily to solve them. I mean, we could always solve them analytically or on computers or whatever. I mean, it's getting the equations of motion that matters. That's the physics, okay? Beyond that, we're just doing solutions, okay? And so in some sense, we're kind of done, but not really, because, we actually got rid of lambda, which allowed us to separate the x double dots and the y double dots. But we're actually interested in lambda because the lambda goes into the generalized force. And so let's go ahead and go after that, all right? Let's pull in the generalized forces. And so that's going to be qx. And I'm just reading off the previous equation for lambda, okay? So it's going to be lambda times df dq, okay? Or df dx and then df dy. And so this is going to be, qx is going to be minus my double dot plus mg times tan theta. That's the derivative of df dx. Okay, and then I have a qy, which is equal to, this because it has a plus out front, it's going to be an my double dot, and it's plus mg, and then df dy is just equal to 1. Okay, and now we can actually plug in for the y double dot, which we did just solve for. And what I'm going to get then, so I have, in fact, let me just show that, right? So we actually have, on the last equation here, we have the equation for y double dot. So we just plug that in. Okay. And what we get is then finally, we get, oops, what's going on here? Get qx equal to minus ma sine theta plus mg tan theta, and I get the qy is equal to ma sine theta plus mg, where a is the acceleration along the wire, so we have to actually get that, okay? So the final step is to get a, and so to get a, what I'm going to do is take my x double dot equation, my y double dot equation, put them into a form where I can add them together, and so that's going to be x double dot cosine theta. So I'm multiplying the x double dot by a cosine theta, and I have got a plus g sine theta cosine squared theta equals 0. I have a y double dot sine theta plus g sine theta sine squared theta. That was the point of multiplying through by cosine and sine, is to get it so that when we add these together, the cosine squared plus sine squared equals 1. And x double dot cosine theta plus y double dot sine theta, so we're just adding these together. And what we just simply get is s double dot. Okay, so that's the path length along the wire, and then that's going to be equal to minus g sine theta, and that's what I'm calling a, okay? And so then this a is what's actually going up into these equations here, okay? So the bottom line is that we've got the actual reaction force of the wire on the bead. In the x direction, we've got the reaction force of the wire on the bead in the y direction. And we also get this equation, which is what you would have gotten in 172 if you'd just done this problem really easily. This is an example where using Lagrange's equations, it kind of blows up on you and gets kind of complicated with multiple equations, multiple unknowns, and you're doing substitutions and things like that. And you're also in kind of an unnatural kind of coordinate frame because you're breaking it up into x components and y components when everyone from intro physics knows that you should just take the distance along the wire. So we do get the final simple answer, but what I would claim is that we now also have this really nice expression for the reaction forces of the wire on the bead, and that is something that would have been much harder to get in just using basic introductory physics ideas. Okay, so that's the example. So that's the first example of using the Lagrange's undetermined multipliers. We applied it to a really simple problem that made it complex or complicated, but in the end we got a simple answer and the extra parts of the physics, which are the reaction forces on the bead. Okay. All right, so that's a simple problem. So now let's crank it up a notch. Let's actually go to something which matters. All right, so example number 2. This is the cylinder rolling down the inclined plane. Okay, classic problem. Okay, because I want the angle that the cylinder is rolling through to be theta, I'm just going to call this the angle alpha. And so then I'm going to put a cylinder on this. It's rolling without sliding. And we have rotational motion and we've got translational motion. So we're going to have both of those contributing to the kinetic energy. But it is a pseudo one-dimensional problem. But we've got translation and rotation, so it's really natural to have two generalized coordinates. So I'm going to pick y to be along the wedge. And so I don't have to pick, a horizontal and a vertical, right? The generalized coordinates, I'm free to do whatever I want. So I'm going to pick y increasing as this moves down the wedge. And as it moves down the wedge, it does so by rolling through angle theta. So that means that my two generalized coordinates are going to be y and going to be theta. All right, so as always, first step is to construct the kinetic energy. So this is going to be 1/2. This cylinder has a mass m to it. I don't think I actually said that, but it'll have a mass m. And then it's going to be y dot squared. That's just the linear speed translational speed, right, going down the inclined plane, and then it is rotating, and so I have to throw in a 1/2 I theta dot squared. For now, let me just keep it as an I. Okay, it is going to be a cylinder. I'll do that in a second, right? We know that that's going to be 1/2 mr squared. But for now, let's just keep it as a y. Now my u, let me go ahead and have the length of this slope, or the length of this wedge, be L. Okay, not to be confused with the Lagrangian. And so this will be, potential energy will be mg L minus y, right? So as y increases, my potential energy gets more negative, and so we've got the sign right on it. But I do have this inclined, and so I have a sine alpha, right? So there's my sine alpha. Okay, so what is my equation of constraint? Well, in this case, it's really simple, right? So let me put that in red. My equation of constraint is that as y increases, it's increasing as the arc length of r theta. Okay, and you do sometimes have to kind of look at that, but if you think about it, if theta goes around 2 pi, that means that I've got a full circumference of translation, and so that means my y has increased by 2 pi r, okay, through one circumference, right? So one rotation. And so therefore I can write my equation of constraint, which has to be equal to 0, so I'm just going to write this as f equals y minus r theta, and that's equal to 0. Again, consistency is important. I could have said r theta minus y is 0, and that's fine. It just puts a minus sign on everything. You try to do it consistently, and so I tend to make my first variable, my first generalized coordinate, something which has nothing in front of it, like in this case, or in the last case, it was y minus tan theta x. This is now y minus r theta. It's just how I like to do it. You're free to flip that if you want, but I try to make that first generalized coordinate the one that when I take a derivative, I just get a 1 out of it. I don't know. It's just consistency, right? It's just one less thing to make a mistake on. All right, and so that means that I can actually now write the Lagrangian. So let me actually write the Lagrangian for this. It starts to kind of blow up a little bit, but it's not bad. So it's going to be L is equal to 1/2. Looks like, okay, yeah, actually it's going to be 1/2 m y dot squared plus, now let me just go ahead and take the 1/2 mr squared for the moment of inertia, and then with the 1/2 that becomes a 1/4 mr squared, and then I get theta dot squared, and then I have minus mg, because I'm subtracting off the potential, times L minus y, and then sine alpha. All right, so there's my Lagrangian. So I want to put that into my Lagrange equations for y and for theta. At this point, I'm not going to write that down explicitly, so I'm just going to start to plug things in and start writing down what comes out of the Lagrange's equations. All right, so it's going to be m double dot minus mg sine alpha minus lambda equals 0, and I'm going to get a 1/2 mr squared theta double dot plus lambda r is equal to 0. And I'm going to go ahead and do my third equation already double derivative, and that's going to be, and I'm going to even rewrite it like this. So theta double dot is equal to y double dot over r. Okay, and so that the third equation is the double time derivative of my equation of constraint. Okay, just like we did last time. Okay, so I can just start to then do substitutions to solve this, and so let me do it over here. And so it's going to be lambda is equal to minus 1/2 m y double dot, and then y double dot is equal to 2/3 g sine alpha, and theta double dot is going to be 2/3 g over r sine alpha. And then finally, my lambda, in fact, do I have an equation of constraint? Yeah, okay, so I ran out of room. Let me do it on the next page. And so then let me go to my Q's, my generalized forces. Okay, and so I'm going to have Q sub y is equal to lambda df dy, which is lambda, which is minus mg sine alpha over 3. And I have Q theta, and you kind of can guess that if I have a generalized force in the theta direction, that's probably has units of torque. So lambda df d theta, that's equal to minus lambda r, and then this is equal to mg r sine alpha over 3. And in fact, it does actually have units of torque. And so what we've actually derived here, the second one, is this is the actual torque, which is causing it to roll. And then you might sort of ask, well, what's this Q sub y, which is the force pointing up the wedge? That's the force of friction. Okay, so we've actually, in the process of doing the Lagrange equations with equations of constraint, not only did we get the standard solution, in fact, I'll actually show it here. I mean, so this was actually the standard solution that we would have gotten with just intro physics ideas, okay? But the intro physics, we had to do free body diagrams. We had to explicitly draw the force of friction because that was causing the torque, and you know, that was a fairly complicated problem to do in intro physics. And yet what's happened here is just by kind of plugging and chugging. I mean, so you set up your generalized coordinates carefully, and they're simple, y and theta. You find your equation of constraint, which is just the arc length that the thing rolls through. And beyond that, you're just kind of plugging it through the equations, and what pops out are these is the explicit expression for torque and also the explicit expression for the force of friction. So while it gets, well, actually, I wouldn't say it's more complicated. I would argue that this is simpler than the approach from introductory physics. I think this, because you're sort of staying in your lane. You're not trying to balance forces per se. You're just solving for 3 equations for 3 unknowns, and then when you're done, you interpret those equations. And you can also look for limits. So you can look for minus sign mistakes. In this case, the force of friction is actually pointed back up, against the direction of motion, and that is exactly what the direction of the force of friction. We could also do R cross F, make sure that the torque is actually the fact that it has a positive sign on it, that in fact we are actually introducing positive angular momentum. And if you do the right-hand rule, I can't really do it here without being in front of you, but yeah, the right-hand rule actually works out, and so the torque actually does have the plus sign in front of it, and so it's a positive quantity. And so you can actually test your limits. Okay, so that's the end of the second problem. And next, let's do a pulley. Pulleys are always fun, right? So let's do a pulley problem. This will be number 3. So in this case, let me set this up as a massive pulley. And what I'm going to do is I'm going to actually wrap a rope around it. Actually, I'm going to wrap a rope around it. So I kind of like draw it like this, right? So there's going to be this rope that's wrapped around it, and then comes off, and then I've got a mass mg, or a mass m, which is then experiencing the force of gravity. Okay, and so there are 2 types of motion. There's the rotational motion of the pulley about the axis, and you've also got the translational motion of the mass. Okay, and so this pulley, we're going to give it a moment of inertia I, and I've already given the mass of little m to the little mass that's pulling on the rope. Just for fun, let me put my generalized coordinate y upwards. You know, you could just as easily say it's increasing as it goes downwards, all right? So now let's just say it's increasing as it goes upwards. As long as you're consistent, so you define the orientation of your generalized coordinate, as long as you're consistent in your equations for kinetic energy and potential energy, you can't go wrong, okay? Now the other degree, or not degree of freedom, there's only one degree of freedom in this problem, but the other generalized coordinate will actually be theta, okay? So we can write down the kinetic energy. It's going to be the rotational part, 1/2 I theta dot squared, or actually I have to give this a radius r. And then there's a translational kinetic energy, 1/2 m y dot squared, all right? So there's our kinetic. Our potential energy is just going to be mgy. It's because I had y increasing upwards. And I have my equation of constraint, which I'm going to write. And again, this is just the arc length, right? As y increases linearly, it's directly equal to the arc length of the rope that's coming off of the pulley, right? That's unwinding off of the pulley. And so that means that this is just y minus r theta. Okay. And so, as I said, I'm just going to start just plugging into Lagrange's equations with the multipliers. And so then this will be, in fact, let me change my color here. So this is going to be I theta double dot plus lambda r equals 0. I'm going to have m y double dot plus mg minus lambda equals 0. And then the double derivative of my equation of constraint, y double prime equals r theta double dot. Okay, so I've got my three equations, three unknowns. From intro physics, you actually would recognize the first two equations where you'd recognize that lambda is actually the tension. Okay, and so this is a case where the undetermined multiplier is just going to directly be the tension on the rope. Okay, and in intro physics, you had to put that in explicitly and draw your free body diagrams, and there'd be one free body diagram for the falling mass. You'd have another one for the pulley. The mass one would be giving you linear acceleration. The one on the pulley would be giving you, torque and angular acceleration. And you had to put that all together. Well, now it all just drops out almost trivially, right? You just solve three equations, three unknowns. Almost don't need to go through the algebra anymore because it's all just standard. And so let me just write down the solutions, okay? And so it'll be that theta double dot is equal to minus mgr. Okay, there's your torque, and then here's your total inertia, because you've actually got this extra term due to the fact that the mass is actually displaced from the center of the pulley. And so this is basically a torque over the total inertia. And then in my y double dot, I get that this is equal to minus g, and I have just 1 over 1 plus I over mr squared. And so again, if there was no rope, it would just be falling with minus g. But because there's a rope and I have to put kinetic energy into the rotation of the pulley, I have a smaller acceleration downwards. So my y double dot is smaller than g, right? Because there's the extra inertia of the pulley, which means that the linear acceleration downward is actually less than g, okay? And so all those are just exactly the things that we'd expect inertia to do in this problem. So the extra inertia of the pulley is slowing things down, all right? So things are moving more slowly because of that extra inertia. And then we can also get the tension, right? So that means that lambda, just again, with three equations, three unknowns, solve for lambda. The answer here is going to be mg. That would be the tension if the mass weren't accelerating at all. Then I have 1 minus mr squared over I plus mr squared. Okay. And so the tension is actually less than mg because you do have linear acceleration. And so as the mass is accelerating downward, it's relieving, in some sense, the static tension that would have been on the rope if it weren't accelerating. Okay, so mg is the tension if it's stationary, but because it is actually accelerating downward, the tension is a little less. That's the meaning of the minus sign. Okay, so we've got this minus sign. And what's really interesting about this is you can actually go to some nice limits. Like what if the pulley were infinitely massive? So it could rotate in principle, but it just has huge inertia. Well, if I goes to infinity, then basically nothing's accelerating, and your tension just becomes mg. It just becomes the static problem. And so as you increase the inertia of your pulley, your tension goes to the limit of the static tension, which would be mg. And so you can very definitely do that. And it can take the other limit. I can set I to 0. What if my pulley actually doesn't have any mass to it? Okay, there is no inertia to my pulley. Well, then I have 1 minus 1, and there's no tension. And so I just have free fall in that case, right? So I can take I going to infinity, and it becomes the static problem. I can have I going to 0, and it's free fall. Okay, and so it's nice and important to check your limits. You can do the same thing on the y double dot and the theta double dots. You know what happens, you know, if the the pulley has infinite mass, goes to 0 mass. Same thing with the the little mg, things like that. And so you can actually test all the limits. And if you get the standard results for the static case and the free fall case, you can be pretty confident that you did all your math right. All right, so you can be looking at your answer here. You test the limits, and if you get all of the right behavior in the limits, then if this is on a midterm, you don't need to see your grade. You know you've got an A. And that is actually a true statement. In physics, very often, when you're done with the math, you can step back and you do this limit checking and do things behave correctly in the limits, okay, of masses going large, masses going small. I'd have to think, of what other limits there would be. But if it checks out in all the limits and you get all the right limiting behavior to your solution, you can be pretty sure that you're going to get 100% on that problem. And if you get that feeling for all the problems, then you can walk out the door and you don't even need to see the graded exam because you know you got 100%. Physics can be that way, so that you combine, the math. Hopefully you don't make any mathematical errors. You check your limits, and you get what you should, and you know it's right. And this is sometimes different from math, I'd say. Sometimes if you're doing straight math, it's harder to check because you don't have that physical intuition that you can use to check the limits. So that's why in physics, it's sometimes easier to be confident that you've actually got the right answer without anyone checking it for you.